Welcome to our first serious example of looking at time-dependent problems. We're going to be looking at the problem called cyclotron resonance. This is the key feature that is involved in what's called nuclear magnetic resonance. It's also the key feature involved in what's called magnetic resonance imaging, and it's one of the first truly quantum technologies that has made it into the mainstream. It is an example of an exact time-ordered product. So it's going to turn out we're going to be able to determine the time-ordered product of this problem completely and totally exactly. That's a rare thing that happens with physics problems that are time-dependent, and so this one is one of the few cases that we really know exactly what's going on. I hope that you've taken the time to look at those earlier videos. Those are from a MOOC that I have called Quantum Mechanics for Everyone, and even if some of the topics were a little bit elementary, you can see that eventually we get to some pretty complicated stuff after building up through all the different elementary things, and I'm sure that some of the material in those videos are things that you have not seen before, and that is really important background for understanding this lecture that I'm going to be giving you here. So if you have not taken the time to go and look through those videos, it'll take you about an hour to go through all of them. I do strongly encourage you to stop watching this, go back, and please play those videos. Okay, as you saw from those videos, when a spin is placed in a constant magnetic field, it precesses. Now the spin precesses because it acts like a little current loop, and the motion of precession you can think of as looking at the tip of the spin, which you can think of as an effective magnetic needle that describes the current loop. That tip traces out a circle that is perpendicular to the magnetic field axis that it is precessing about. And we had videos that showed you what precession looks like with a bicycle wheel, and we also had them with a gyroscope. And this is the quantum mechanical version. So the magnetic moment of the spin that has angular momentum S is given by mu, that's the magnetic moment, equals gamma times S. And I just want to remind you, we're continuing to use this Gottfried normalization for S, so S is dimensionless. That means the h bar is going into the constant gamma. Gamma is called the gyromagnetic ratio. It's given by Eg h bar over 2mc. G is something that's called the Landé G factor. And for the electron, it's essentially 2. If you take into account quantum field theory corrections, it is corrected on the order of 0.1% or so. The Hamiltonian for a magnetic moment placed into a magnetic field is minus mu dot B0. What that says is that the magnetic moment is going to be aligned in the direction of the field. If it's aligned in the direction of the field, I have the largest positive dot product between the magnetic moment and the magnetic field, and the minus sign guarantees for me that that energy is a minimum. So this is the Hamiltonian that will correspond to aligning those magnetic moments with the magnetic field. When we plug in what the magnetic moment is, we find that we can rewrite this Hamiltonian as minus gamma B0 SZ. That's choosing B0 to lie along the z direction. Of course, this is a very simple Hamiltonian. We redefine the coefficient in front by calling it minus h bar capital omega times SZ, and capital omega is gamma B0 over h bar, and that has a name. That's called the Larmor frequency. If our states had a total spin S and a z component m, then h0 acting on them would give just minus h bar omega m multiplied by the state, because those states are eigenstates of Sz and of S squared. In particular, they're eigenstates of Sz, so the Hamiltonian acts trivially on those states. The time dependence is also very simple. It's an eigenstate. Remember, stationary states, when we look at their time dependence, it just gets given by e to the minus I, the energy, times t. So let's go ahead and work that out for these states. E to the minus I over h bar, h0 hat t, multiplied by the state Sm, and if we plug in what the operation of h0 is on the state, we find it's e to the minus I omega mt, Sm evaluated at t equals 0. So whatever we started with at t equals 0 it will pick up a phase e to the I omega, capital Omega, Larmor frequency times m, the magnetic quantum number, times t. That tells us that the states rotate with a frequency given by the Larmor frequency times m. This rotation is called precession. It's appearing at harmonics of the Larmor frequency, and you saw in the earlier videos exactly what precession is. Again, if you have not watched those videos, I strongly encourage you to go and look at them. Precession is not a very easy concept to understand well, and it's good for you to have a physical feeling for what that means, and you can get that by looking at those earlier videos. Okay, as I had mentioned before, many problems that are time-dependent problems that we care about are problems where we take a time-independent H0 and we add on a time-dependent field. So in a magnetic resonance experiment, we add an additional small perpendicular field that rotates around the z-axis. We're going to call that B1 of t, and it's rotating. So it's in the xy plane, and the direction of the magnetic field is changing as a function of time in a steady fashion, in a steady oscillation as it rotates around in the xy plane. We assume that the second field is small, but its rotation frequency can be adjusted externally. Now, you might think about this and say, well, perhaps something interesting might happen if the frequency of the rotation of that magnetic field was the same as the precession frequency of the spin as it precesses around the magnetic field axis. And indeed, that is the case. When that second field rotates at the same rate of precession, then in the spin's rest frame, it sees a static perpendicular magnetic field, and whenever a spin sees a magnetic field, it will precess about it. So if we wait long enough, something that has a positive projection on the z-axis will precess around the x or y direction in this rotating frame, and we will end up with something that has a negative projection on the z-axis. And that's the same as saying we're going to cause the spin to flip. So that is the process. That's what magnetic resonance is. It's called resonance because I have to match the rotating frame frequency to be precisely that of the precession frequency. And when I do that, something very interesting happens. I'm able to flip the spin. That changes the energy of the system, and I can observe it by observing the energy that is absorbed by the spins as they flip. Now our task is to examine this mathematically. So we start with the magnetic field as a function of time. It's B0 times z, that's the constant large field, plus B1 times x cosine omega t minus y sine omega t. I want to caution you, z hat, x hat, and y hat here are unit vectors. They are not operators of position. So h of t, which is minus mu dot b, simply becomes minus h bar capital omega sz minus gamma b1 times sx operator times cosine omega t minus sy operator times sine omega t. Now we consider the operator that transforms us into the rotating frame of the perpendicular magnetic field B1. This operator we're going to denote as d hat of omega t comma z. That's indicating that we're rotating about the z-axis. The angle of rotation is omega t, and so d hat omega t around the z-axis is equal to e to the minus I omega t times sz. This is a definition of a rotation about the z-axis for the spin. That's why the spin operator sz is appearing in the exponent. So let's evaluate what this rotation does to the operator sz. It means that we're going to have to multiply by a d dagger sz times a d. That's easy to work out, e to the I omega t sz, sc e to the minus I omega t sz. We'll get the same thing for sx and sy. For sz, because sc commutes with sc, that's just is equal to sc. This operator does nothing to the sz operator, and that's not so surprising. If I'm rotating about the z-axis and I have something pointing along the z-axis, nothing happens to it. For sx and sy, now we can evaluate this two ways. You have learned earlier in this class about the Hadamard lemma, and you can see that this is a nice example of the Hadamard lemma, but we're going to actually evaluate it in a slightly different way. This is another technique you can use for these kinds of conjugation operations or similarity transformations where I have a dagger of an operator in between, and a dagger on the other side, especially if those unitary operators in the front and in the end of the expression are expressed as exponentials of Hermitian operators. So in this case, we have e to the I omega t sz times sx times e to the minus I omega t times sz, and we're going to call that fx of t. Now, fx can be an operator. We're just being symbolic now to represent it as fx of t. The thing that's interesting is because this has a time dependence to it, I can take a derivative with respect to that time. And when I do that, I pull down an I omega as I will, because this is the coefficient that's appearing in the exponent. I'll get the e to the I omega t sz, and then you see I'll get a commutator of the sz with the sx. And then I'll get the e to the minus I omega t sz on the other side. But remember, the commutator of sc with sx is isy. Recall again, we're using the Gottfried normalization, so there are no h-bars here. And so dfx dt will equal minus omega fy, where I define fy to be e to the I omega t sc sy e to the minus I omega t sz. Now if I take the time derivative of fy, I'll get an I omega e to the I omega t sc commutator of sz with sy e to the minus I omega t sc. And by working out the commutator of sz with sy, you see that's going to just equal omega times fx. So you see we've developed this second order differential equation for fx. The second derivative of fx with respect to t is minus omega squared times fx. And we get the same thing for fy. This is a very simple differential equation. We know how to solve it. Fx of t will be cosine omega t fx of 0 plus 1 over omega sine omega t, the derivative of fx at 0, and fy of t will have a similar form. Now remember, we know what fx of 0 is. Fx of 0 is just sx. We know what fy of 0 is. It's just sy. We also know what the derivative is. Remember, we calculated the derivative of fx with respect to t was minus omega fy. So that derivative will be minus omega sy for fx dot, and it will be omega fx for fy dot. So we can just substitute all of that in. This is summarized for you here at the top of the page. And when we substitute all of that in, what we find is d dagger sx d is equal to cosine omega t sx minus sine omega t sy, and d dagger sy d is equal to cosine omega t sy plus sine omega t sx. Now if you think about this, this is exactly what you would get if I take the x and y axes and rotate them uniformly with a frequency omega about the z-axis. Okay, so to summarize this, what we find is the Hamiltonian h of t is minus d dagger omega tz minus h bar omega sc minus gamma b1 sx d of omega t sz. How did we get that? We have to go back and take a look at the Hamiltonian itself. I'm going to scroll back there now. You can see that that Hamiltonian has a term in it that was sx cosine omega t minus sy sine omega t. When I use this d and d dagger, you see that's going to be exactly sx. Of course, the sz is unchanged. Now, what we've done here is really quite remarkable. We have taken this time-dependent Hamiltonian and using this similarity transformation, or if you like, a unitary transformation, we have re-expressed it as a time-independent Hamiltonian. This is called going into the rotating frame. And as we had mentioned before, if I go into the rotating frame that rotates at exactly the frequency of this perpendicular rotating frame, that rotating magnetic field no longer looks like it's rotating. It looks like it's just pointing in one particular direction. And indeed, that's exactly what's going on, so you shouldn't be surprised that we're able to transform this time-dependent field in this fashion. But we're going to find that this makes solving the problem really simple. We're going to write that the wave function psi of t is equal to d dagger of omega t about the z-axis multiplied by psi rotating of t. So psi of t is the Schrodinger time-dependent wave function for the Hamiltonian h of t. So we're going to operate h of t onto psi of t. We're going to need that for the Schrodinger equation, and that is going to give me d dagger minus h bar omega sc minus gamma b1 sx times a d and a d dagger, but the d dagger equals 1, so I can get rid of them. So that operator acts directly on psi r of t. And of course, that whole thing is equal to minus I h bar d by dt psi of t. That's just the time-dependent Schrodinger equation. We're going to multiply both sides now by d. The left-hand side is simple because d times d dagger is also equal to 1. So we just get minus h bar omega sz minus gamma b1 sx acting on psi rotating of t is equal to I h bar d of omega tz, d by dt, d dagger of omega tz, psi rotating of z. And we can calculate that derivative. Remember, d dagger is a time evolution operator. We know what its derivative is. It's just going to pull down an sz. And so what we're going to find, and of course remember the sz commutes with the d, and so d sz d dagger just becomes sz. So one of the terms when we take the derivative, when the derivative hits the d dagger, it's going to give us this first term, minus h bar omega sc times psi rotating of t. And then of course we're going to have the term where the derivative hits the rotating frame, I h bar d by dt. We're left with a d dagger, but d dagger equals 1, so we can get rid of that as well. So we end up with this relatively simple equation, and notice I can take that first term, the minus h bar omega sz, and pull it over to the left-hand side. And now we have a fully time-independent Hamiltonian acting on the psi r of t, and it's equal to this time derivative. Of course, since it's a time-independent Hamiltonian, it's easy to solve. Okay, so what we have is this psi rotating of t. We can write it as e to the minus I over h bar t, h acting on psi rotating of 0. We can use just h. It's really h prime because it's not our original Hamiltonian, so we'll call it h prime. But we can use this effective h just acting on the state because it's time independent. Remember, we were able to work out exactly what the time evolution operator was when the Hamiltonian was time independent. It simply was e to the minus I over h bar t times that effective Hamiltonian. All right, that's it. We've essentially solved the problem. Psi of t then becomes d dagger omega t z acting on this psi rotating. We can plug in those two terms. We find psi of t is equal to e to the I omega t sz, e to the minus I t omega minus omega sz minus gamma b1 over h bar sx, all of that acting on psi rotating. If you think about this for a moment as well, think about e to the I omega t sz. That is e to the minus I h0 over h bar times t. So this other piece that we have here is actually the interaction representation time evolution operator. What is surprising about it is that interaction representation time evolution operator is so simple. Okay, so you can also think about what we've done as going into the interaction representation, and the surprise in this problem is that the interaction representation time evolution operator is the time evolution operator of a time-independent problem. All right, now suppose we start our system in some pure state, Jm at t equals 0. What is the probability for it to go into another state at time t? We'll call that p of t starting in Jm going to J prime m prime. And the probability will be the overlap of whatever the wave function is with J prime m prime and the modulus squared of that. Now, this Hamiltonian commutes with s squared because it's just composed out of sx, s, and sz. And anything that commutes with s squared cannot change j, so the j must be the same. So we'll get a delta jj prime that comes out of that. And because it's an eigenfunction of sz, the first term, e to the I omega t sz, I can operate that on the left. It'll give me e to the I omega t m prime. But that's just a phase that factors out, and the modulus squared of that phase is equal to 1, so I can remove that term as well. And so we're left with calculating this one complicated object. Now think again back to when we were doing the spherical harmonics from operators. This is very similar to what was being calculated in that case. We have this complicated exponential we need to evaluate that's acting on this term Jm, and then we need to take the overlap with Jm prime and just figure out what that is. Okay? So calculating this result in general is complicated. You might think that we could use exponential disentangling. I actually think we can use that, but I'm not going to do this problem that way. I'm going to show you the standard way that you'll find in all kinds of textbooks. You might want to think about how it might work by using exponential disentangling. It could be a neat exercise for you to see how well you understand how we work with operators by trying to work that out for yourself. Don't worry, I'm not going to give it to you as a homework problem to do that, but you might find it interesting to work that out for yourself. We're going to now take a look at the simplest case, which is spin 1/2, and I'll just review for you what this is because we're using the Gottfried normalization. So SZ is 1/2 sigma Z. That's 1/2 1 0 0 minus 1. SX is 1/2 0 1 1 0. It's 1/2 the sigma X. And if you recall, we have this expression e to the I v dot sigma is cosine v plus I sine v multiplied by v dot sigma over v. We derived that earlier in the class. So what we find, we can immediately get, we have to identify what is vx and vz in this v dot sigma. So we look carefully at the exponential. We find that the modulus of v is equal to t over 2 square root of omega minus big omega squared plus gamma b1 over h bar squared. We're going to call that capital delta times t over 2. Capital delta is equal to that square root. Then e to the minus it omega minus omega sc minus gamma b1 over h bar sx is going to equal cosine delta t over 2 times 1 minus I sine delta t over 2 times omega minus big omega divided by delta times sigma z minus gamma b1 over h bar delta times sigma x. Now I can just substitute that into this expression. Okay? So if I want to ask how likely is it to flip the spin, I will start in the state with the spin up. That's the 1/2 1/2 state. I'm going to act these operators on it. I'm going to look at the overlap with the 1/2 minus 1/2 state. Now the term with the 1 has no overlap because the 1/2 1/2 state and the 1/2 minus 1/2 state are orthogonal. The sigma z also has no overlap. The only term that's going to give me an overlap is the sigma x, and I can read off what the coefficient is. It's sine delta t over 2 gamma b1 over h bar delta. I have to square that, so I get sine squared delta t over 2 gamma squared b1 squared over h bar squared delta squared. That's the probability of going from plus 1/2 to minus 1/2 as a function of time. You might ask, what is the probability to stay in the 1/2 state? Well, we can work that out as well. You find that that's going to be cosine delta t over 2 minus I sine delta t over 2 omega minus big omega over delta, the whole thing modulus squared. That's going to give us a cosine squared plus a sine squared. And if you work out using the fact that cosine squared plus sine squared is 1, you can rewrite that as 1 minus gamma b1 over delta h bar squared sine squared delta t over 2. But of course, that's exactly what it has to be because these two probabilities must add up to 1. And so, indeed, we verified that this works. Okay, that is it for cyclotron resonance. Working out the general formulas, if you want to work them out in terms of the angular momentum spin matrices, actually gets quite complicated. I suspect, however, I've not done this myself yet, but I strongly suspect that if we use exponential disentangling, we can actually work out what the cyclotron resonance is for all spins all at once in one shot and would get an interesting formula. It would, however, involve evaluating some kind of polynomial expression, just like we had to do for working out the spherical harmonics. I'll let you think about that. I think it's kind of a cute thing that we can actually solve a much more complicated problem using that nice disentangling operator that we developed earlier. Okay, that is all for this lecture.